Thank you all for staying up to now. This will be the first session of the connectivity. This will be more focused on Wi-Fi, and later my friend James will talk about BLE. Wi-Fi 6. Short agenda. First of all, intro to what is Wi-Fi 6, and then what does Wi-Fi 6 try to solve, and then Wi-Fi 6E, what does that mean, and then how does TI products relate to Wi-Fi 6. In general, typically, when we talked about Wi-Fi in the past, it was all about throughput. It means that in every new generation that we have, we try to improve the throughput of the performance in the Wi-Fi. And you can see that between A, G, N, 11AC, AX, and then coming soon, BE. What's interesting is that Wi-Fi also understood that after working on NAC and AX, people don't really understand what Wi-Fi is trying to do. So Wi-Fi invented a whole new way of defining the Wi-Fi specs. They said we're just like iPhones. We will have Wi-Fi 4, Wi-Fi 5, easy numbers. As we go forward, it means that it's probably better and improvement. Today, most of the world is exactly transferring from Wi-Fi 4, Wi-Fi 5 to Wi-Fi 6. What is Wi-Fi 6 actually trying to solve? If you think about it, what does it help us if you buy the fastest car and you're stuck in traffic? I guess in Singapore, they just built the F1 track, so you have no issues of where do you run your fast cars. But otherwise, where do you use such fast when you have a congested environment? And this is what happens today. In today's world, we have more and more places where we have more and more connections. In the past, in our home, we had a computer, a laptop, we had maybe a tablet that we used to connect to the Wi-Fi network. And for that, throughput was important to get the best experience. But in today's world, we have more and more solutions connected to our home access points. We have our printers, we have our home appliances, we have our IP cameras, and all those things together. Even in my house, I already have more than 20 devices connected to the access point. What happens when all these devices are trying to transmit at the same time? That's where the efficiency of the network is dropped. And this is in the home, and of course, when you go to much more like public places or people where more people or more devices exist, the overall efficiency is much lowered. What we see is Wi-Fi in the past, the legacy devices, it's called CCA, which means listen before talk. How does Wi-Fi know when to transmit in the air? Wi-Fi devices, the different Wi-Fi devices, sensed the medium, understood that nobody is talking, the medium is quiet, and therefore I'll start to transmit. All that works great when there are few devices that are doing this in the same time. But what happens when you have 30 devices that each are waiting for the medium to be quiet, but suddenly more than one decides to transmit at the same time? That's when you start having collisions and you're starting to have retries. And because even when you have the next number that you are able to decide that maybe I should transmit now, you have a chance of transmitting with a collision with another of the 30 devices out there. So what we see is that when we have so many devices, Wi-Fi 4 throughput is around 25 megabit per second. What Wi-Fi 6 does is fundamentally changes the way the Wi-Fi channel works. It's not listen before talk anymore, is that the access point has the actual capability of deciding who transmits when. That means that the Wi-Fi access point tells, okay, I have so many channels trying to talk to me at the same time. I will split the airtime between those different users and therefore create a much more cleaner channel for each one. With that kind of management, the overall throughput of the Wi-Fi 6 on the same scenario is almost 6 times better. from 25 megabit per second to 160. So how does the Wi-Fi access point capabilities change in order to reach this kind of throughput? So one is the management itself, as we said. It's called trigger frame. And the second is working not OFDM, but OFDMA. What is the main difference between OFDM and OFDMA? OFDM, at the end of the day, only one user can speak at a time. It means that if we look at the air, you have user 1 can talk, only afterwards user 2 can talk, and between that, we have all the collisions. In OFDMA, what actually is enabled because of the fact that we have resource units that are allocated inside the channel is that multiple users can use the same channel at the same time. If you think about it, sometimes we have small packets, sometimes we have large packets. For example, in the TCP protocol, when we typically want to, let's say, download a file, each packet will be around 1,500 bytes. But giving back the acknowledgement of, hey, those 1,500 bytes have been received, the packet size is only 40 bytes. So if you think about the listen before talk that we said before, it doesn't matter the size of the packet. Once you are both competing over the air, you use all the medium. But now, if you're able to allocate the channel to different people by how much throughput they actually need, if I have such a small packet of just an ACK, I can use only a limited number of resource unit and give all the other allocation to a different user and have an overall efficiency which is much higher than having them one by one. So Wi-Fi 6, every time people say what is the number one added value, one is trigger frame, second is OFDMA. As you can see also in the picture here, the users can start moving up front much faster due to the fact that they can do concurrent. Another important feature is, okay, Wi-Fi was able to help and create OFDMA, but can I also have multiple stations transmitting in the same time towards the access point or receiving? And that is what is called multi-user MIMO. So multi-user is the fact that even though we are at the same 20 megahertz and it's the same time period, we can actually talk to different devices at the same time. And that is another capability of Wi-Fi 6. And of course, this increases the capacity of the channel because now on the same 20 megahertz, he can talk to 4 or 8 stations at the same time and create different higher speeds for specific users. Another important feature is BSS coloring. So what Wi-Fi understood is that one of the main problems is if I have an access point, let's say in a company's office, and I have multiple access points, Wi-Fi signal is strong, and because I do sensing of the air, if I just sense that the medium is busy, I won't transmit. But sometimes the station itself that is transmitting is not transmitting to me as an access point, but is transmitting to a different access point. And that access point might be 20 meters, 40 meters away from me and is transmitting to a different access point. So in the past Wi-Fi, we used to be quiet because we do listen before talk. Now, what is happening with the BSS coloring is the fact that, as you can see in the picture, what you can see in the picture is that the access point is working on a specific channel. So if I have 64 and 64, all those stations that are around, let's say where the 100 is, will listen. Both 64 channels will still be able to get the Wi-Fi transceive, and actually all the area will be quiet. But now with BSS coloring, I'm able to declare to which access point I'm actually connected to. So access points that are farther away have a different color and therefore can actually transmit and receive at the same time. So in this picture, you can see the blue here. So the blue is a different color. So all the stations that are actually connected to the gray 64, if they see that the medium that is busy is because of the 64 blue, they will continue transmitting as usual. So this is another level of trying to make sure that the overall efficiency of the network is increasing. Also, Wi-Fi 6 is adding improvements for power. One of the features that multiple people are talking about is called TWT. TWT is target wake time. What this does is enables users to create a negotiation with the access point and declare when is the next time they will transmit or receive data from the access point. So up until now, the rules in the Wi-Fi were that you have to synchronize with the access point every beacon or every DTIM. Inside the DTIM, there was an information element that used to declare, hey, I have data for you, please be awake and ask for the data. So the user needed to wake up every 200 milliseconds in order to receive those DTIMs. Here with the TWT, you have an option to negotiate upfront for the access point and say, okay, I will be away for an hour, for 2 hours. Please don't try to send me anything because I'm away in a sleep mode. And just when I wake up after those 2 hours, please see if any information needs to be sent to me. And you can declare different TWTs for different users and therefore decrease the power, because during your sleep time, you're in a lower power mode and don't need to be connected. A few comments on TWT. So Wi-Fi spec is working perfect. The issue, of course, are real-life scenarios, because multiple times we come to customers and when they start thinking about their own use case, TWT becomes slight of an issue. If you think about a doorbell, so sometimes, or an IP camera, so sometimes customers would like to open their phone and understand what's happening now on the camera. So if you want to understand what's happening now, the device cannot be asleep for 1 hour and only then you will get the picture of what happened an hour before. So the TWT use cases have to be also make sense from a customer perspective on what exactly can the product go to sleep and what is the actual effect. So we do have customers that are using this like for temperature sensors on trucks. So for example, the truck needs only once in a few hours to download all the measurements that happened before that. That could be a good use case. But every time you have some kind of two-way communication that is needed in a much more bounded time, TWT is not the right solution. Other features that Wi-Fi 6 have is range improvements, which means there's a DCM mode that you're actually duplicating the data on a pair of subcarriers, and there's extended range, which means that you repeat part of the packet in order to be able to detect it and analyze the packet even if you're farther away. Any questions up to now? Wi-Fi 6 also understood that, okay, now we have the 2.4 gigahertz, we have the 5 gigahertz. But what is the main problem with the 5 gigahertz? So when you talk about high throughput channels, you would like to have 80 megahertz channels, 160 megahertz channels. But the Wi-Fi understood that when you look at the 5 gigahertz, in real life, you only have one 160 megahertz channel, and you have barely 4 80 megahertz channels. So even though you have the wide channels in your house or in offices, you don't have anywhere else to run. You don't have other channels to move to. So at the end of the day, you're stuck with everybody still transmitting on the same channel. That's why Wi-Fi worked to enable the 6 gigahertz band. So if you look at the US, they opened up from 5.9 till 7.1 as another 1.2 gigahertz. And what we see is that this actually enables 7 160 megahertz channels. So now all the problems that where do we transmit without having to avoid collisions? With the opening of this new channel, it's becoming a whole different ball game. And also in Europe, so they started by opening the first 500 megahertz, which also increases the Wi-Fi 6, and now Wi-Fi Alliance is working with the EU in order to open more channels for the 6 gigahertz. So what this does is it enables the collision and the avoidance to be much less, because now Wi-Fi can pick different channels where there's less people working on them and be able to transmit in the best possible channel with minimum channel collisions. Our new product, our Wi-Fi 6 product, is coming after many years of TI being in the Wi-Fi 4 world and being part of the biggest companies on the cell phones, home appliance, and others. That's why we understand what it means to have reliable Wi-Fi, which means that it's sometimes, even when you pass Wi-Fi Alliance certification test, there are always true IOP issues with once you go and put your product in the market and you sell millions of units, millions of households, and then each access point acts a bit different. And that's why also internally we have our IOP test lab, which has more than 230 access points in order to ensure the customer experience. That means that any access point that you have at home, we probably already tried to connect to that access point, make sure there is no connection issues, transfer an iPerf, make sure that the data throughput is stable, and have a whole suite of tests versus that access point. So once the product hits the market, it's not that it just works in a Wi-Fi Alliance very basic setup, but it also works with real-life access point and has been checked and validated. This also shows the stability of the features and makes sure that the product is working. Wi-Fi typically comes in two ways on how to add Wi-Fi to a product. The most simple, or let's say how the phones, computers, and all the last generation product works, is the fact that there was an external MPU or an external MCU that did a lot of the heavy lifting of the work of the product, and then customers wanted to add Wi-Fi to their solution. For that, that's what we call the companion IC. It means that device itself just does the Wi-Fi. Another segment is the wireless MCU. The wireless MCU is where also you have an M4. In the future, we will have an M33. And that Cortex can also run your simple application. If we think about a smart plug, or if we think about simple products, you do not want to have an extra MCU in the system just to run some basic functionality. So this MCU in the system can solve your problem and make sure that it runs in one device. And this, of course, also includes all the software layers. Is it the TCP/IP, TLS, MQTT, HTTP, anything that needs to be connected in order to reach the cloud. So our previous devices, this was exactly the CC33 33XX family. Those are the companion ICs. And the 35XX, those are the family of devices that will have the MCU integrated. And they are a continuity of our current product line that's called 32XX that has the M4. As mentioned with the MSP M0, TI is trying to create now affordable devices. So this device too is very, very competitive in order to win and enable Wi-Fi to any product. This is supposed to be true differentiation, not only because of the capabilities, but with the pricing. And this is built on years of experience in order to make sure that the solution is working with the RF, with the operating temperature, and having all the features of the last Wi-Fi 6. Another point is that this solution can be attached to different MCUs, MPUs, and OSs. So we try to build the system in order to be flexible. So whatever MPU or MCU you have in the system, we will have a way in order to add Wi-Fi to your solution, and supports multiple OSs and multiple configurations of internal or external supplicant to simplify your software design. And of course, it has the latest connectivity standard, the Wi-Fi 6. It's multi-band 2.4 and 5, and in the future also 6 gigahertz. And the product itself is backward compatible with 11N and the Wi-Fi 5 20 megahertz. The device itself doesn't do only Wi-Fi, but it also does BLE. We had multiple customers coming and saying, okay, Wi-Fi is great, but we still need BLE for commissioning in order to enable the product to connect to the network. Or we have, for example, a thermostat where we want the thermostat to be connected over Wi-Fi, but we have a few temperature sensors in different rooms that we want to connect through battery-operated BLE. For that, the product also supports Wi-Fi and BLE, BLE 5.3. The device itself is a controller of the BLE, which means that the host will run on the MC or the MPU that is attached to, and the device itself will run the BLE 5.3. In general, how does the product look? So the product itself, you can choose how do you want to connect from an interface perspective. If you are a high throughput kind of solution and you have SDIO, you can choose SDIO. If you are trying to have a smaller bandwidth and different size of number of pins, you can choose SPI, depends on your solution. The BLE itself is typically run over the UART, but we do have customers requesting that the BLE should run over the SDIO, and that is possible too. The device itself supports coexistence, and the coexistence can be or internal coexistence between the BLE device and the Wi-Fi, or external coexistence for customers that want to add a different technology, Thread, or others in Zigbee. Except for that, we have the 2.4 and 5 gigahertz antennas and the power management in order to enable the device. The device itself has 2 power rails. One is the 1.8 and the second is the 3.3. The package itself is a 5x5 and the modules are 11x11, and the 2.4 and 5 gigahertz are pin-to-pin, so people can start with one and upgrade to the second in a simple solution. Security, because everybody needs to talk about security. Code and data security. So the device itself, which is another advantage, is 100% RAM-based. Previous devices were ROM-based. Customers were requesting to have a more flexible solution that if we need to do updates, if we need to do changes, the product itself, longevity will be much longer if we will have a product that is much more RAM-based than ROM-based. So the upload itself of the device on the RAM is done by checking that the code itself that is actually coming from TI. That means that TI signs the code and ensures that only TI code can run on the TI device and that it's not coming from any other source. The second thing is in security, there is always a question, how do you do rollback protection? The reason for rollback protection is, for example, if in image number 3, somebody found a flaw, and now you have continued to image number 3, 4, and 5, you are always afraid that somebody might upload image 2 again and try to create and use that flaw in order to get into your device. For that, we also have a rollback mechanism over the OTP bits of the device. That ensures that if there is a security vulnerability that you want to protect from, there is no issue and you always are running on the latest secure version. The second is physical countermeasures. we had customers saying, okay, almost everything we are running from a higher level, let's say the actual application is running over TLS or of other security methodologies, so there is no need for security or less need of security. But what happens when you boot up the Wi-Fi and you want to give the password of which access point to connect? And you are afraid that people will sniff the actual SDIO lines or the interface to try to understand the password. For that, we have an option to encrypt the interface of the SDIO for specific messages in order to ensure that that information is passed in a secure manner. Last is the Wi-Fi security itself. So for that, this device supports all the latest security features coming from Wi-Fi Alliance, WPA3. And of course, internally, we are protecting the credentials so people cannot understand the keys internally in order to use and activate software that is not supposed to run. Any questions on the security? So if we look at what TI had in the past, TI had a companion family that we used to call WireLink 8, and we had a SimpleLink family that was the Cortex M4 running with the Wi-Fi solution. So today we try to simplify, we just call everything CC. And we still have the two families of devices. One is the companion ICs, which are in order to connect to any MPU, MCU, and that is the 3301 family, 3351 family, and in the future for the 6 gigahertz, the 3361 family. And in parallel, we are working on our MCU solution that is already going to be available soon, and that has the MCU and the Wi-Fi together inside a single chip. Any questions?
Has there been a big effect of the range of the access point as the frequency has increased from 2.4 to 5 to 6 to 7?
Can you repeat the question?
The access point that you're using, the router, the range.
So the range is not relevant to this specifically because the range is more relevant to the output power that you can actually transmit. The output power itself is typically limited by regulation, FCC, ETSI, and others. So you're still stuck at, let's say, 21, 22 dBm output power for the access point. So that doesn't really assist in order to solve that if you're trying to solve the range problem.
Hey, Uri. So if you're looking for 80 megahertz and 160 megahertz, is our only option to transition to the 6E, the 6 gigahertz chip, or does TI have any offering that will be able to support 80 and 160 megahertz at Wi-Fi 6?
Currently not. Okay.
So it's just 6E, or it's not in the roadmap?
One second. It's two different questions, okay? One is the band that the Wi-Fi works, and the second is how big is the channel that the Wi-Fi will work on. Mm-hmm. So TI does have a plan to support Wi-Fi 6E and to be able to receive and transmit in the 6 gigahertz band, okay? But if somebody, just like in Wi-Fi 5, wants an 80 megahertz channel, that is a different type of throughput and a different type of device than just adding Wi-Fi to your use case. And for that, it will take more time for TI to support an 80 megahertz channel inside 5 or 6 gigahertz. But we do have on our roadmap to support the 6 gigahertz.
Okay, thank you.
And the throughput of even supporting 20 megahertz, the throughput of a UDP, for example, is around 60 megabit per second over the SDIO, and TCP can be something around between 40 and 50. So it's not, the throughput is pretty high also for a single band 20 megahertz.
Sure.
And the good thing, another important part is that once you support Wi-Fi 6, even when you have those big channels, the access point can divide the channel and say, okay, I have now a tablet or I have now a television that supports the full 80 megahertz. Then I will allocate 60 megahertz out of the 80 for the TV or for anything else, and I will leave the 20 megahertz for the home appliance. So the fact that it's now OFDMA gives a lot more flexibility to the access point and how to solve the use cases in order to create the overall efficiency. So even if I support only 20 megahertz, the access point still has a capability of restructuring how he wants to transmit or receive the data, so we can also assist in the overall efficiency. Any more questions?
One quick question about feature. So currently, is there any chips that's able to support the Google Fast Pairing service?
That's more of a software question. Okay, it's not a device question.
Oh,
and then
okay.
So it's like we don't do anything not to support it. Okay, but it's more about getting the whole framework set.
Okay, sure. Thank you.
In general, most of those questions like DPP and things like that, all the new methodologies are more software based on the higher levels of the Wi-Fi than the specific packets that come to the Wi-Fi solution itself. Okay, that's where most of the complexity is. Last comment before I pass to my friend James is that today we already have all the evaluation kits. That means that anybody that wants to start testing, running, showing, demonstrating. So there's two ways to do that. One is to pick BeagleBone Black, Citara MPU. We already also have it with AM62, and we have also working with other vendors that are not TI based on Linux in order just to add Wi-Fi to those solutions. Or we have, for example, the AM24, which is a MCU-based solution. That means that the Wi-Fi can run with an RTOS device. And how does that work with our CC33XX family? So as I said, we also have a new M.2 card, so it connects nicely and seamlessly with AM62. And we have everything needed from a software, hardware, and training in order to get you started. Any last questions?
Library code?
Yes. So when you're working with an RTOS, what we have is a very simple 7-8 APIs that covers all the Wi-Fi around it. So for example, you just have simple APIs like Wi-Fi on that turns on the device, and then Wi-Fi scan to understand which access points do you have in the area. And then you have wireless connect. Just give the AP access point name that you want to connect to and a password. And then you just have commands of send and receive. And you can have a very simplified driver that you can port to any OS that you want. This example is on FreeRTOS. We already have customers that port it to Zephyr and to ThreadX. And with those simple API commands, they're able to enable the Wi-Fi solution. Any last questions? Thank you very much.